How to calculate dose and AUC of CR formulations. Control release formulations. The main aim of this control release formulation is to maintain the steady state at a desired concentration level. So the drug is slowly released or controllably released so that the steady state is maintained at a desired concentration level. And this can be achieved by controlling two aspects. One is the proper dose, and second one is the dosing interval. So based on the nature of the drug, we can fix what is the required dose or whatever the required dosing interval to maintain a particular steady state concentration levels by control release formulations. So here we can use one of the equation, F into X naught, that is the total amount of the drug that is going to be absorbed, is equal to CSS, whatever the desired steady state level required, into tau. Tau is the dosing interval, which is multiplied by CL, that is the clearance. So by using this equation, we can calculate what is the dose required or what are the dosing interval required to maintain a particular steady state concentration. So in this video, let us see how can we calculate this dose as well as the dosing interval by using this equation. So let us start with the first working example 1. How much dose of a sustained release preparation is required at every 12 hours to attain a steady state plasma concentration of 2 mg per liter? The clearance of the drug is 18 liter per hour and 90% of the drug is absorbed. So let us see what is the data given here. Tau, that is the dosing interval, is given as 12 hours, and CSS, steady state concentration, as 2 mg per liter, and clearance is given as 18 liter per hour, and fraction of the drug absorbed is equal to 90%. So here what we have to calculate is what is the dose X naught that is required to maintain the steady state concentration. So let us see the solution to this working example 1. Again, let us see what is the data given. So tau, CSS, clearance, and F values are given. Now we can use this equation, F into X naught is equal to CSS into tau into clearance. So by substituting the values in this equation, F is nothing but 90%, which is equal to 0.9. So 0.9 into X naught is equal to CSS is given as a 2 and tau is given as 12 and clearance is given as an 18. So now 0.9 into X naught is equal to 2 into 12 into 18. Otherwise, X naught is equal to 2 into 12 into 18 by 0.9. So by solving this, we will get the answer as 480 mg. So 480 mg of the dose of the drug should be given in order to maintain a steady state concentration of 2 mg per liter for every 12 hours. So for every 12 hours, 480 mg of the drug should be given to maintain the steady state concentration of 2 mg per liter. Let us go with another example. A 600 mg of the sustained release product was given for every 12 hours. If the volume of the distribution is 20 liter and elimination rate constant is 0.5 R inverse and 90% of the drug is absorbed, calculate the average steady state plasma concentration. So here the data given is X naught is given as a 600 mg, tau is given as 12 R, and volume of distribution is 20 liter and elimination rate constant as 0.5 R inverse, and fraction of the drug absorbed is 90%. Here what we have to calculate is the steady state concentration that can be achieved with the dose of 600 mg and dosing interval of 12 hours. So let us see the solution to this example. The data given is the X naught is given, tau, volume of distribution, elimination rate constant, and the fraction of the drug absorbed are given. Now which equation we can use? F into X naught is equal to CSS into tau into clearance. But here clearance is not given. And already we know that clearance is equal to Ke into Vd. So by substituting in this equation, we will get F into X naught is equal to CSS into tau into Ke into Vd. Now all these values are given and we can easily calculate what is the steady state concentration that can be achieved with these parameters. So let us substitute in this equation. So 0.9 into 600 is equal to CSS into 12 into 0.5 into 20. So in other words, CSS is equal to 0.9 into 600 by 12 into 0.5 into 20. By solving this, we will get the CSS is equal to 4.5 mg per liter. So for this drug, we can achieve a 4.5 mg per liter of the steady state concentration when 600 mg of the drug is given for every 12 hours. And here you can see that the drug is not completely absorbed, only 90% of the drug is going to be absorbed. Let us go with another example. A 300 mg of the dose of a drug is given every 5 hours until a steady state level is achieved. At steady state, the AUC for one dosing interval is 50 mg per liter into R. So what is the average concentration over the dosing interval? This is a different question, and here let us see the data given here. X naught is equal to 300 mg, tau is equal to 5 hours, and AUC is equal to 50 mg per liter into R. So what we require is the CSS, that is steady state concentration. Now let us go with this solution. So data given is here, three parameters are given: X naught, tau, and AUC. So which equation we have to use? The previous equation what we have seen is not suitable for this calculation of this example, because here AUC is going to be involved. So how can we calculate the AUC? AUC, area under curve for one dosing interval, is directly proportional to the steady state concentration in that interval. So AUC is directly proportional to CSS. So when the CSS, the steady state concentration, is multiplied by the dosing interval, we can get the total area under the curve in a particular dosing interval. So AUC is equal to CSS into tau, where AUC is the area under curve for one dosing interval. Now by substituting this equation, AUC is equal to CSS into tau, that means 50 is equal to CSS into 5. Otherwise CSS is equal to 50 by 5, so which gives the 10 mg per liter. So the steady state concentration maintained within that period is the 10 mg per liter. Finally, let us go with another example. A 500 mg of the dose of a drug with clearance 5 liter per hour is given to maintain an average steady state concentration of 10 microgram per ml. If the fraction of the drug absorbed is 0.7, the dosing interval should be. So here the dose is given, X naught is equal to 500 mg, CSS 10 microgram per ml is given, clearance is given as a 5 liter per hour, and fraction of the drug absorbed F is equal to 0.7. Here we have to calculate how much of the dosing interval is required to maintain the steady state concentration around 10 microgram per ml. So let us see the solution for this. So data given is X naught, CSS, clearance, and F is given. Again we can use this equation, F into X naught is equal to CSS into tau into clearance. So F is given as 0.7, so 0.7 into 500 is equal to CSS is given as a 10. Here CSS is given as a 10 microgram per ml, which can be converted into 10 mg per liter. Both are same. So because the clearance is given in the terms of liter as well as dose is given in terms of mg, we can convert the CSS from 10 microgram per ml to 10 mg per ml. So now CSS is 10 into tau into 5. So in other words, tau is equal to 0.7 into 500 by 10 into 5. So which on solving gives 7 hours. So the drug should be given for every 7 hours to maintain a steady state concentration of 10 microgram per ml at a dose of 500 mg. So in this way we can calculate what is the dose required or the dosing interval required, or what are the AUC that is to be maintained in a control list formulation by using this equation, F into X naught is equal to CSS into tau into clearance. And area under curve for one dosing interval can also be obtained from this equation, where AUC is equal to CSS into tau. The calculations with the control list formulations are just similar to the conventional dosage forms, where we can use the same equation, F into X naught is equal to AUC into clearance, but here the AUC is equal to CSS into tau. And here control list formulations are given at the multiple doses separated by a specific dosing interval in order to maintain the steady state concentration. And again we have to remember that the steady state cannot be achieved immediately after this administration of control list formulations, and as with the conventional tablets, it requires at least 5 half-lives in order to achieve the steady state concentration. Sometimes a loading dose may also be included in the control list formulation so that the steady state can be achieved immediately by immediate release of the loading dose and a control release of the maintenance dose. So here whatever the calculations we have seen are mainly related to the dose that is to be maintained in order to achieve the steady state concentration. Importantly, the control release formulation cannot achieve the 100% bioavailability, so the F value is also important in estimating the dosing interval. So by using these equations, we can calculate what is the dose that is to be required for a particular drug to maintain a steady state concentration, and what is the dosing interval that can be maintained so that we can achieve a desired steady state concentration. And when our clearance is not given in the equation, we can calculate the clearance from the volume of distribution and the elimination rate constant, as CL is equal to KE into VD.